Yeah, good afternoon. Yes, I will talk about this freeform similar as the talk before, freeform micro-optics, but I will go to the use case of optical communication. I think there it's less of making an image or making something on the road. It's more about making low losses, having no losses, and ease of kind of fabrication and packaging. So I will do that in really talking about the wafer scale in-plane micro-optical interconnects that we did for the fiber arrays. Okay, after the short introductions into optical packaging, I will explain our idea, the concept, design. We'll talk a bit about fabrication. We'll show how we did characterize our devices, show the results, how we ease really fiber assembling, and I will finalize with some outlook, some possible application of our device, and a short summary. Good. Everybody knows, I think one of the most challenging steps in optoelectronics industry remains the photonic packaging, especially if you have fiber arrays, if you have multiple fibers and not just one. So normally what you end up is also we have quite bulky devices. Assembly processes are often quite complicated. It requires alignment normally even in 3 up to 6 degrees of freedom. So it really ends up with quite a high fabrication cost. So how are we tackle this? We are going to use micro-optical elements, which are very compact, which can be directly integrated onto wafers. We do the optic interconnections kind of in plane, so we don't stick out, so it really stays in plane. And we will include this kind of comb-like structure, so to ease really fiber alignment. So that really makes plug-and-play passive alignment possible and will reduce the costs massively. Okay, then to the idea, the concept of our device. It's basically it's 2 parts. One is the reflecting surface, it kind of here and on front here and side view, which redirects the light that comes from the fiber to our optical device. Could be a photodiode or some grating just lying on our wafer, as well as these fiber walls called here, which will align the fiber precisely to our device. So, and this orange part, that's our kind of free-form optical device, nicely seen here. Of course, we would like to be this device compatible with all kind of standard fibers that we have, this kind of single mode, multi-mode, covering the whole optical communication wavelength range. And what we also can do, of course, by properly designing our reflecting surface, to direct the angle, how we are going to in which angle we are going to redirect the light to the wafer. That's especially important if you have grating couplers, which needs certain angle to be most efficient to couple light into the waveguides. How are we fabricating it? We have already seen a little bit before the process from SUSE. It's very similar. It's kind of a 3 steps. So first we need a master that more or less has the shape of our reflecting surface. We do that with photolithography process for photoresist. We just illuminate through a mask and ending up with some cylindrical shapes. Then we go to a reflow oven so that we have nicely spherical shaping more or less lens type structures. Of course, if you want to have other forms, then you could, instead of spherical, you could have direct laser writing to make these masters. As there are other originators in fabless actually involved, they can do anything. If you have this master, out of it, we are going to do a stamp. So it's quite similar. We're going to use a mask, kind of chromium. You will see the mask, what's the purpose of it. Have some UV curable material in between, and by demolding, we end up with a stamp. And this stamp then is now used for mass manufacturing, because we can just do the UV replication on several wafers if you treat the stamp well. So again, you put on some UV curable glass-like material, align your stamp to the wafer with your structures that you had in mind, illuminate again, and harden it. The illumination points, you demold and develop all what's not hardened, and you will end up with the structures that you can nicely see in these CSEM pictures. It's quite a big one with big alignment fiber walls on the side, fiber inside already put inside. The reflecting surface here in the front. We do have process given some residual layer, and this is actually one that was put on a peak with integrated waveguides. We did also realize these structures on glass wafers. Here with the top mask I was talking before, you can have any shape from the top. So instead of just having this square, you can have some funnel-like structure, so that will ease then the fiber inserting in the structures. Or you can even have some additional ones that for stress relief, to that the fiber is really not being stressed inside here and even going to break away. So then it's quite good, quite flexible with this kind of structures. Here it's a little bit smaller one than the one before, so we can really implement bigger or smaller structures. Then we did characterize the whole devices here on a glass sample. So what we did, we have an input fiber, a single mode fiber, and an output fiber on a 90-degree angle. And by measuring the losses that goes through it and is redirected to the multi-mode fiber, we were seeing that we reached quite nice losses. So it's in the tens of dB range. And by doing some kind of Y and X sweeps at different set differences of this output fiber, we were proven that the beam quality was quite nice, because it really follows exactly more or less the theoretical expanding of the beam. And we were able to see how under which angle our surface redirects the light using the X direction. Here is we put our structures on grating waveguides with input and output, and which has some kind of a S shape, so that you don't measure straight a light that is just going straight. And here we had a little bit more losses. It was in the range of 10 dB. But that was due to, we had this question before about the shrinkage. We took into account that the shrinkage in vertical direction, but we kind of had the shrinkage also in a horizontal direction that we have. We kind of did not took correctly into account, so that's these structures are not well aligned because of the difference in horizontal. So that's one cause of the losses, but we think that we can go to much lower losses. Here you can see on the left side the introduction of a single fiber. It really works quite easily. It's a little bit more complicated if you have a 12 array, because to handle 12 fiber ribbon, it's a little bit more difficult. But you can see here it's kind of partly inserted into this array and then pushed forward. Still, it is quite it's good possible to do. We realized in a demonstrator, so we had 12 fibers inside, glued them, had a ribbon cable with the connector on the other side, and when you put the white light into the connector, then you can see the light coming out under this more or less 90-degree in the back of the glass piece. Good. With that, I already come to the kind of the outlook. And application field. One, it's quite obvious. If you have a single photodetector or VCSEL, then you can use this kind of structures. If you have an array, it's even more. The benefit is even higher, because then you can have fiber ribbons, as it is shown here. But you can also interconnect silicon nitride photonic integrated chips, so you can make connectivity to chips, array connectivity. You could also think of a backplane connector, so you have two boards that with an additional lens could ease alignment tolerances, because you have a broad beam here and have a board-to-board interconnectivity. But also there you can think of kind of a connectivity to waveguides in optical board, which is quite recent, quite interesting, and kind of a very promising field. Or of course then going directly chip-to-chip interconnect, as it is shown here. So this technology can really have a lot of application in the communication. Okay, to summarize, we presented an innovative, compact, in-plane optical interconnect. It is fabricated in the promising cheap UV imprint technology. We showed losses in a quite low range. This structure can also be implemented with alignment features to ease the packaging. Also, again, reducing the cost of fiber packaging. And we demonstrated some first devices for coupling light into silicon nitride waveguides. So with this, we really think this micro-optical interconnect can be implemented for industrial volume production, and it will facilitate integration packaging of electro-optical components. And with that, I come to the end, and thank you.